Okay, this is the last section of chapter 6 on projectiles, and it's the projection motion, projectile motion formula, or sometimes called the equation of motion for a projectile. There is no new content. This is about actually writing a single equation which we can derive from the horizontal and vertical components of the motion of a projectile. Now remember, there are a few things that we said were true, and that is that the horizontal and vertical components we need to work out separately. So let's do something like that. We know that the only thing that links the two is time. So let's say that the only thing that we had was this: an initial velocity of u, an angle of projection of, let's call it alpha. Okay, and then all we knew is, right, okay, let's call the vertical displacement y and the horizontal displacement x. So horizontal displacement we will call x, and the vertical displacement we're going to call y. So how far across and how far up. And what we're going to do, we're going to write down an equation for the horizontal and make t the subject. We're going to write down an equation for the vertical and make t the subject, and then put the two together. So let's start with our horizontal. Now for our horizontal motion, using speed, distance and time, I want an equation for the time. So that's going to be the distance, and this is going to be x, this is how far it's going across, divided by the velocity or the speed, and that's just going to be u cos alpha. Okay, so here I've got an equation for my horizontal with t as the subject. I'm going to do the same for the vertical, and where I have t in my vertical equation, let's spell vertical, right? I'm going to replace it and substitute it with x over u sine alpha. You'll see what I mean in a moment. So let's have a look at our vertical motion. And let's say I want an equation, or let's write down what we've got. So the displacement is going to be, and I'm taking upwards as positive, my displacement is going to be y. How far up has it gone? U is going to be u sine alpha. V, well, we don't care about that, we don't know what it is. A we do know, that's going to be negative 9.8 for acceleration, so negative 9.8. And for the time, I'm going to take what I had for the time for the horizontal. So this is going to be x u cos alpha. Now I'm going to put the two together over here, and that gives me an equation that puts together the horizontal and the vertical. So I'm looking for an equation that has s, u, a and t. So if I use s equals ut plus half at squared, s is going to be replaced with y, u is going to be u sine alpha, t is going to be x over u cos alpha that we got from the horizontal, plus half times negative 9.8 times by let's get rid of this, t squared, so that's going to be times by x over u cos alpha squared. Now what I've done here is I've got an equation, I'll tidy it up in a minute, that has both the vertical and the horizontal, because I've got x in there, and I could rearrange this to make x the subject or make alpha the subject. Loads of things you can do with this, and in its simplified form you could actually remember the equation and use that to help you answer the questions, but it's just as easy to use that. So let's tidy this up and see what we get. So you get y equals, now what's going to happen here is that u and that u will cancel out. That will leave me sine over cos, so that'll be x tan alpha. So x tan alpha, that's what the whole of the beginning bit becomes. And then I'm going to have minus 4.9, and if I square that, I'm going to get the fraction x squared over u squared cos squared, so you square everything there. Now what we could even do, the x tan alpha we'll leave like that. Where I've got this cos squared at the bottom, you can change it, you can write it as sec squared. So you could even write it, it's not really simplified, but in a slightly different way. You could then write minus 4.9 x squared over u squared, you can't really do anything with that, times by sec squared, like that. So either one of those two you can use as what we call for our equation of motion. And what that does, it gives you a single equation that has the x and the y displacement in. You could memorize that equation if you like, and then just substitute in what you know, because you can find the x displacement if you know the y displacement, the angle of projection, the initial velocity. You can find anything, as long as you have just one unknown, you can find the others. Yeah, so useful if you want to memorize it, but it's not necessary. But what you will be asked to do in the exam is to sort of manipulate this, yeah, and maybe derive it. So in the exam they may say, okay, can you derive this formula, can you show that this is true? So you'll have to go through this process by writing down in terms of t what's going on horizontally, and do the same for vertical, and then you're pretty much done. So this is very similar to what we just did. It's basically answering the question with no numbers. You'll notice here we have initial velocity is u, the angle is alpha, this range here is given as r. There are no numbers, so you're basically just going to be given an algebraic answer. Right, so in part A we want to find the time of flight. So that's basically, right, how long is it in the air in part A, and it's going to be in the air as long as the vertical displacement is not 0. So what we're going to do in this part of the question is we're going to be looking at the vertical upwards as positive. So the time of flight is going to be between the times when s is 0. The initial velocity is going to be big U, because that's what they've used, sine alpha. V we don't care about. A is going to be negative 9.8. I should put that on my diagram. Always going to be negative if you take upwards as positive. and the time of flight is big T. So all we need to do now is to put that into a Suva equation that has S, U, A and T. So that's going to be S equals UT plus half AT squared. So 0 equals U sine alpha times by big T plus half times by negative 9.8 times by big T squared. Oh right, I missed a bit out here. It says that we're going to be using G for gravity. So what I'm going to do in the next bit is just replace that with the letter G. So I don't need the 9.8. So let's tidy that up. So we have TU sine alpha, and then we're going to have half G or minus half G. Actually, let's write it as half times by negative G times by T squared. Okay, so tidying that up a bit more. TU sine alpha minus G over 2 T squared. So I'll basically want to make T the subject, so I'll start by factorizing it. So T U sine alpha minus G over 2 T. Now that's going to give me two values for T. T is 0. Now that's not the time of flight. That's just going to be basically right at the start when the displacement is 0. It's the bit in the brackets that will give me the time of flight. So when that is equal to 0, the bit in the bracket, that will give me the time of flight. So U sine alpha minus G over 2T equals 0. From there, we just need to make T the subject. So T will equal, so if I take the U sine theta across, or U sine alpha, sorry, across, and then divide that by G over 2, which is the same as timesing by 2 over G. So there we go. That's the time of flight. So if we knew what U was and what the angle was, then we've got the time of flight. Yeah. Okay, part B. Just give ourselves a bit of space. In part B, the range on the horizontal plane. So the range is going to be the the horizontal distance from the point of projection to the time it lands on the ground. So remember, we're using speed, distance and time because the speed is, or velocity is constant. So the range is basically like the distance, isn't it? So when we get that value there, that's the distance. So what's that going to be? That's going to be doing the speed times the time. So the initial speed is going to be U sine, so U cos alpha, times by the time. So the time that it's in the air, right? We've got that from, we just worked that out, didn't we? That's that there. 2U sine alpha over D over G. 2U sine alpha over G. Okay, so this is what R is. So let's tidy that up a bit. So we'll end up with 2U squared sine alpha times by cos alpha divided by G. So doesn't matter where we put it. over G. Now, you may or may not notice that this bit here is half of the double angle formula for sine. So if I had sine 2 alpha, that would be 2 sine alpha cos alpha. So I could, if I wanted to, replace the sine alpha cos alpha with half sine 2 alpha. Now if I do that, the half and the 2 will cancel out. Just leave me with, you don't have to do this unless the question said write it in this form, u squared sine 2 alpha over G. So you don't have to do that, but you know, if you needed to prove that, then you would leave it in that form. So answers are here, that's RT, and R is here. So it's basically what we've been doing before, but with no numbers. Okay, last example here. Part A of this question here, this is identical to what I did on the first slide. So I'm not going to do this again because it's exactly the same. The only difference is that, I don't know if you'll remember, you might need to go back, that here we had sec squared alpha because we had cos squared at the bottom, and you'll know one of your identities is 1 plus tan squared alpha is sec squared alpha. So that's just one more step onto what we did on the first slide. So it's identical to that. So I won't be doing that bit again. Part B is just substituting the values into that formula we've got. So u, from what I've got up here, I can see that u is 28, so that can be substituted in. I have the angle alpha is just given as alpha, and what we know is that when the horizontal distance is 32, at the same time the vertical or the horizontal distance, sorry, the vertical distance is 8. So those values can be substituted in so that we can find alpha. So this just came from the question as well. When the horizontal displacement is 32, the vertical displacement is 8. So we'll just plug those in. So this is quite easy once we've done part A. So part B, 8, so just substituting in, is 32 tan alpha minus G. I'll leave it as G as the moment because that might cancel out somewhere. I don't think it does, but we'll leave it like that for the moment. G times by 32 squared over 2 times 28 squared, and that's times by 1 plus tan squared alpha. So I'm guessing we want this to look like a quadratic. So 8 equals 32 tan alpha. I'm going to work out all of this here and expand the brackets and see what that is. So all of that there just becomes 6.4. So expanding the brackets as well. So minus 6.4 minus 6.4 tan squared alpha. So this is a quadratic we want to solve, so I'm going to rearrange that. So I have 6.4 tan squared alpha minus 32 tan alpha and plus 6.4 plus the 8 equals 0. So let's put those together. 6.4 tan squared alpha minus 32 tan alpha, and 6.4 plus 8 is going to be 14.4. Now, like a previous example, I'm not going to try and factorize that. So I might say something like, well, actually, I could say that, let x equal tan alpha. So it then becomes the quadratic 6.4x squared minus 32x plus 14.4 equals 0. Although I'm going to use my calculator, I would write down that x would equal minus b, so minus negative 32 plus or minus the square root of b squared plus 4ac all over 2a. I'll just write that down for the examiner. But I'm actually going to use my calculator to get my two values of x, in other words, my two values of tan alpha. So let's do that. And doing that, I get 9 over 2 and a half. So I get 9 over 2 and a half. So if I just do the tan inverse of those, I'll get my answer. So changing my calculator back to calculator mode. So tan inverse of 9 over 2 gives me 77.47. So let's call that 77.5 degrees. Let's call that alpha 1. And my other value will be the tan inverse of a half. And I get 26.565. So let's call that 26.6. So 26.6 degrees as my other answer. So again, although I'm doing it on the calculator, I still write down my working. Yeah, so still write down this bit here. Don't just do this and work out on your calculator and write the answer down. You'll get credit for this. Yeah, because you don't want to just do everything on your calculator, write it down and get it wrong. You'll lose marks. Right, so now you should be able to do exercise 6D on pages 123 to 125 of the textbook.